Hi everyone, welcome to section 11.5, our fifth section in chapter 11. We're going to talk about probability models in this section. The first thing we want to do is we want to look at situations to see is this fair? Would it make a fair decision? You guys do this all the time as students. You just do it subconsciously, intuitively, without thinking. Teachers oftentimes have to consciously come up with ways that are fair, making decisions that are fair. So let's talk about a few scenarios and decide, is this a fair way to make choices or not? For instance, you have a class of 25 students and you want to choose 3 students at random to have to bring food for a class party. And we want this to be random so that we're being fair to everybody. Any 3 sets of students then should have an equal chance of being chosen if it's fair. And that's the point. So let's look at this one. What would result in a fair decision? So let's say the teacher lines everybody up alphabetically and then flips a coin. So for the first person in line, you flip the coin. Heads, you have to help bring food. Tails, you don't. And then go to the next person and the next person and the next person until you have 3 people to bring food. Would that be fair? And hopefully you can see absolutely not, because if your last name starts with Z, you can pretty much be guaranteed you won't be picked. And if your last name starts with something early in the alphabet, you are much more likely to be picked. That is not a fair way to do it. So that's not a good model. Let's do this. Let's have each student draws a card from a well-shuffled deck, and everybody has their card. And then the teacher shuffles a second deck of cards, shuffles them really, really well, spreads them out, and she draws one by one until she pulls a card that matches somebody in the class. They get chosen. They are going to bring food for the party. Does it again until she gets a card that matches somebody else's card in the class. How does that sound good? Yeah. Assuming it's a good shuffle, that would be completely random, so that would result in a fair decision. All right, that's the kind of thing that you're going to be looking for. So here's to see if you understand it. 2 siblings are trying to decide who has to mow the lawn this weekend. They decide to race, and the winner does not have to mow the lawn. Will that result in a fair decision if they use a race to determine who mows the lawn? Think about it. What do you think? I would think right away, no, that's not fair, because most likely one of them is a better runner than the other, and they'll win every time. If the 2 siblings, though, are super evenly matched and they win about half the time, always when they race, then it might work. So it really depends on the 2 siblings. Do you see that? So answers could vary in that kind of situation, in which case I would have to look at your explanation if I asked a question like that on a quiz or on a test. Okay, another thing that we can do to be random is to use random numbers. And you can generate random numbers through your calculator. You can generate random numbers on your computer. You can print them out. Sometimes you can even find them in the back of textbooks. And you can use these generated numbers then to choose students. Here's an example of what a lot of times randomly generated numbers look like. Often they're just digits, 0 to 9. And they often are grouped in groups of 5 just to make them more readable. So I'll put a couple rows of randomly generated numbers on the board. Okay, here's some randomly generated numbers, not too neatly written, but you can kind of see what they would look like. And let's say a coach has this on his clipboard, and he wants to select 3 out of his or her 15 basketball players at random to lead warm-ups before practice each week. So what the coach does is assign each player a number from 0, 1 to 15. Each player has a number from 0, 1 to 15. So how can the coach use a random number table to choose the 3 players? Well, they're numbered 0, 1 to 15, so what the coach can do is just take a list and just divide it into 2-digit numbers until he or she gets 3 numbers selected. So 87 would not work, either would 49 or 43 or 97, because those are not in his list, but 07 is. So there would be the first student chosen. And then 20 would not work, 52, 59, 57 up, but 04 would be the second player chosen at random. Do you see how we just divided it up into 2 digits? 48, 36, no, but the next one is 12. I ran out of room, sorry about that. The next one is 12. So the player 7, player 4, and player 12 would be the totally randomly selected students to lead the warm-ups before practice for that week, or whatever the coach wanted them to do. But that's how you can use randomly generated numbers to make a selection. It's not the only way, but it's one of the ways that you can. Let's say a teacher wants to organize 10 students into 2 teams for a math game. And so she, of course, or he, it doesn't matter, assigns each student a number from 0 to 9. And we're going to use the second line. The teacher decides to use the second line of digits to pick the 2 teams. And what the teacher's going to do is alternate the assigned team each student is chosen. So first number is team 1, second number is team 2, team 1, team 2, team 1, team 2. If it's a number that's repeated, obviously you're going to ignore it. Okay? Do you see what we're doing? First number is team 1, second number is team 2, third number is team 1, next number is team 2, next number is team 1, next number is team 2, unless it's a repeated number, and then in case it's the next one. And then you see what I mean? So the next non-repeated number. So with that thought in mind, with that strategy in mind, could you tell me which numbers are going to be used to create team 1? We're going to use this second row right here. Which numbers would be team 1? So pause the video at the screen looking at these numbers so you can see them. Work your way across and figure it out, and come back and see if you got it right. There's team 1. Team 1, team 2, I have to ignore that. Team 1, have to ignore that, Team 2, team 1. So there's our first 3 numbers, ignore that. Team 2, ignore that. Team 1, do you guys see how that works? Team 2, and then team 1. So you're ignoring repeated numbers and you're moving to the next one. It's a little complicated, but I think this one was probably easier. But that's, hopefully you got that worked for you. Okay, and then you can have a probability model to determine things as well. A probability model is you make a simulation experiment to represent what you're looking for. So let's say, here's what I mean. A restaurant like Burger King or something gives away 4 different toys in their kids' meals. And there's 4 different ones, and your kid, of course, wants all 4. Or your kid brother, kid sister, somebody wants all 4 of those toys. It's really important to them. Each meal contains exactly 1 toy, and they're equally randomly distributed among all the kids' meals. So about how many kids' meals would you need to buy in order to collect all 4? So what you can do, rather than buy a whole bunch of meals, is kind of figure it out, is you can create or do a simulation. These type of numbers could be a simulation, but we're going to do an actual simulation experiment, something that could represent, remember, the 4 toys. So you could find a spinner that has 4 sides to it, 1, 2, 3, 4, and you can just spin it and keep a tally of when you get 1, 2, 3, and 4. Each one of those can represent one of the toys as you spin your spinner. Right, here's your spinner. There we go. There's your spinner. Each time you spin it represents one of the toys, and you keep track until how many spins did it take until you got at least each number once. So in the example in the book, this one was 2, this one was 3. Finally, they got a number 3. This one was 2, so they realized 5, 6. It took them eight total spins to get one of each number. So based on that experiment, you would think, okay, so I'll have to buy about 8 Happy Meals or whatever in order to get all 4 prizes. That could be what you conclude. The thing is one trial is not going to really do it. You really want to do more of these if you depending on how accurate you want to be. So you should repeat this simulation several times, and or have a whole group do it and then compile all your results. So let's say you did it, and these were all the ones you got: 7, you got 9, 12, 6, 15. I mean, you got a lot of different results each time you did this. 5, 8, 10, 7, 5, 8, 10, 7. All right, what would you do then to know, well, how can you know about how many meals you would have to buy? What you would do is take all those results and find their average. And I believe when you find the average, it ends up being about 9.08. Now, that's a lot of work. It's very possible that the company that owns that restaurant and that puts those prizes in thinks about these things because they know kids will motivate their parents to buy them and they want them to buy as many as possible. So they're going to make 4 different toys to get them to buy that many meals, or maybe 5 different toys to get them to buy that many meals. Does that work better than offering one meal, one prize one week, another prize another week? You see what I mean? What will generate the most sales? People think about this and they run these kind of experiments to figure that out, and in order to get you to buy their Happy Meals or whatever. It's a real thing. They got it for this one. Suppose you are playing a board game and you have to roll a 6 before you're able to move your man out of start. This sounds familiar, doesn't it? So could you come up with a simulation to predict the number of turns you would have to take before you can move a man out? And just how many you can do theoretical, or you could do a simulation. So that's it. You can figure that out on your own. That's okay. Let's talk about using probability to analyze decisions and that kind of thing, because that's what people do. We are going to talk about, let me put some data on here. Okay, a pharmaceutical company is trying to test the effectiveness of a drug, and this is done. Blind case studies, a lot are done. You have this illness. It looks pretty serious. Would you be willing to participate in a blind trial of an experimental new drug? And people say, yes, I'll do anything to try to get some help. And they're given this medicine, and it is totally blind, or at least should be. You don't know if you're getting the actual drug or if you're getting a placebo. Even the person giving you the medication cannot tell. It's all coded with numbers and stuff so that nothing will taint the results. But they do this, and here is what they found. This means their symptoms improved. Their symptoms did not improve. And then these are my totals. So this is a two-way table between the drug and the sleep drug and placebo, improved or not improved. And this is the information. And they had 160. 80 of them took the drug. 80 of them didn't, and these are the results that they recorded. So what's the probability then, now that we've looked at this, what's the probability that a volunteer did report noticeable improvement in symptoms given that he did receive the drug? Okay, so given that he did receive the drug, or she, what's the probability that they noticed improvements? So of those given the drug, 67 out of the 80 noticed improvements. That is the probability, 67 over 80. And what percentage is that? That's about 83.75%. Okay? So that's how you could look at that. What's the probability that a volunteer received the placebo given that he did not report a noticeable improvement in symptoms. So the ones that, there's 69 did not report a noticeable improvement in symptoms, and of those, 56 got the placebo. Is that what we asked? That they got the placebo given that he didn't report. Yes, so 56 out of the 69. So of the 69 that did not notice improvements, 56 got the placebo. So that would be 56 out of 69, and that is that probability, which is about 81.16%. Okay? This is a review of some of the stuff that we did before. And that helps when reading it, using a two-way table to find that kind of information. All right, they decide this drug is effective. We're going to distribute it. We're going to make money. We're going to advertise it. This is going to work for us. And it's marketed as an effective way to improve the symptoms given this type of illness. In this case, I think it's asthma, based on asthma. I guess I could have read that, huh? Did the company make a good decision? Do you think that they were right? What do you think? Yeah, they did make a good decision, actually. Because if you looked, those who received the drug did receive a noticeable improvement, and those who did not. You can see a definite difference in this. So yeah, it didn't work for everybody, but it helped a good percentage. So yes, I think they made a good decision. Okay, I'm not going to do the got it today just for sake of time. You guys can look at that and figure that out on your own. And your answers may vary. Anyway, you would have to justify it yourself. So I'll let you work on that and figure that out and do the online and practice it and see how it goes for you. But that is it for section 11.5. So have fun with the written and the online, and I'll see you guys next time. Bye for now.